Welcome back everyone. In the last lectures, we have seen how to find out the solution of the state equations that we had and also the output equation. We found out a method of diagonalizing the matrix, and when diagonalizing was not possible, we made the matrix or transformed the matrix into a Jordan canonical form, and using that also we could find out the solution of the state equations. While explaining about the Jordan canonical form itself, you saw that I introduced few terms like kernel, generalized eigenvectors and all. And by now you should realize that linear algebra is going to play a heavy role in modern control theory. And that is the reason this is the right time for me to introduce some of the concepts of linear algebra that will be required in this course. Of course, remember this is not a exhaustive list of concepts that would be required in this course. First thing that we are going to deal with is the set of real vectors Rn. And what is Rn? Rn is a vector of this form where there are n number of elements, say a1, a2 to an, and where all the elements here are real numbers. Let us consider the set of real vectors Rn and the set of real numbers which we are calling as scalars. Now, we can define two types of operations on these two sets. One is called vector addition, which means I take two or more elements from this set of Rn vectors and then I add them up, okay, that we will call as vector addition. And the other operation is called scalar multiplication, where I take one element from the scalars and then one element from the vectors and then we multiply them, that is known as scalar multiplication. This is something you are quite used to, so you should be able to understand. If I suppose take 1, 2, 3 which is a vector in R3, I can always multiply with 2, this will give a new vector in R3. Similarly, if you take 1, 2, 3, you can always add up with say 3, 0, 1 which is another vector in R3. So, these are operations you understand well. This set of real vectors Rn over R, basically over the scalars, is called a vector space. Okay. It is a special property of the set. It is called a vector space if it satisfies 10 properties. Which are the properties? Number 1 is that when you add 2 elements from this set, the new element that you will get is also in this set, which is true, right, for Rn. If you take 2 elements from these vectors and you add them up, so u plus v, that must be equal to v plus u, which is again true, you understand that. Then associativity u plus v plus w is equal to u plus v first and plus w. Similar, then comes the idea of existence of additive identity. So, there is a element here which when added with any other element in this set will always give you the give you that element back. So, for example, if you, so the additive identity element is here is 0 0 0 0 dot 0 plus any vector you add, you will always get back this vector, that is called additive identity. So, this set has an additive identity. Further, there is an additive inverse also. So, if you take any vector in this set, you can always find out another vector in this set which when added with that element will give you back 0. So, these 5 properties. Then we have the property of closure of scalar multiplication, that is, if you take any scalar and multiply it with a vector here, the new vector that we will get will also lie here. If you take multiplication by 1, say, so if you take the real number 1 here and multiply it with any vector here, you will get back the vector again. Third property is, if you take 2 elements from here, say alpha and beta, and you perform this operation. So, beta into u you perform first, where u is a vector here. So, when you multiply that with alpha, you will get back the same thing as alpha into beta into u. Then comes distributive property. So, alpha times u plus v, where u and v belongs to this set, is equal to alpha times u plus alpha times v, and then you have second distributive property which says that alpha plus beta into u is alpha times u plus beta times u. So, all these properties are satisfied by Rn over R. Okay. So, all these properties are satisfied, and that is why Rn over R is a vector space. Okay. Now, intuitionally, what is the meaning of this? Basically, if you take anything in the set, if you add them up, you will get back something in the set itself, and intuitively what it means is that if you take any two elements from the set, you add them up, you get back an element which is in the set. You take any element from the set, scale it up or down, the new element that you get will be in the set. If you take any element plus alpha times of another element from the set of Rn, will give you another element in Rn. So, it is closed in that sense, and that is a special feature. Okay. Remember, we started with a set. Okay. Remember, the basic entity, mathematical entity here is a set, okay, and this set has some special property over real numbers. The properties are the ones that we listed down, and that is why we call this not just a set, it has qualified to become what is called a vector space. Okay. Now, I will give you another example where what I will do is, let me change the scalars to complex numbers. Okay. Now, if I change the scalars to complex numbers, let us see whether all the 10 properties are satisfied or not. Okay. The set, the vectors are still from Rn, but the scalars I have changed to complex number now. Now, if you look at that, you will see that all the properties here, all the first 5 properties here which was basically based on vector addition are anyway satisfied in this case. So, no problem. However, as soon as you go to the closure under multiplication property, notice that if I take a complex number as a scalar, say suppose I take j, you take another vector v1 here, say v1 is 1 0 0, say from R3. So, you can see that j times 1 0 0, the new element that you get is j is 0 0, which is not an element in this set. So, you can see directly that one of the properties is not getting satisfied in this case. So, hence therefore, we can directly say that Rn over C is not a vector space. Notice that Rn over R is a vector space, but Rn over C is not a vector space, right. What about Cn over C? You can check that Cn over C will also be a vector space. Okay. Now, here is something for you. Why do not you try Cn over R? Okay. Check whether Cn over R is a vector space or not. Okay. You check it on your own. Mostly in this course we will be dealing with real numbers. Okay. So, it will be the vectors will be real numbers, the scalars will also be real. So, what is important here to understand is that Rn over R is a vector space. Okay. So, this is what vector space is all about. So, basically vector space is nothing but a set with some scalars and these two operations that we have defined, that is vector addition and one is scalar multiplication. These 4 things. So, if I write it down, it is like Rn is the vector space here, are the set of scalars, and then you have vector addition, and then you have scalar multiplication. These 4 things together is the vector space. Okay. So, but in general, while we in general talk about vector spaces, we will just directly say that Rn is a vector space. So, in that case, you should understand that by default I am talking about the scalars to be real numbers. Okay. Because every time telling Rn over R is a vector space becomes difficult. So, we just say that Rn is a vector space, which means Rn over R is a vector space. You should, that is by default, you should understand that. Okay. Now, once you have a set, okay, from set theory you know, suppose you have a set, you can always talk about subsets. Okay. Now, what we have shown is that when we have taken this set was special in the sense that this set over real numbers was a vector space. It has a special property that if you add them up, it will come back to the same set and all those closure properties were there. Now, if set has subsets, then vector space may also have what is called subspaces. So, what is a subspace? So, suppose Rn is your vector space here. So, within Rn there can be a set, say W, okay, which is a subset of Rn. Okay. Now, we will call that W is a subspace of Rn. W must be a vector space over R. See, remember Rn was a vector space over R. So, then W should also be a vector space over R. So, basically you had a vector space over R, inside that there is another set which also is a vector space over R. Okay. Let us take an example and understand it. So, suppose I am talking about R3, okay. You know what R3 is. R3 is basically the set of vectors of this form where x, y, z are real numbers. Okay. And you can also understand that R3 over R is a vector space. R3 over R is a vector space, right. So, now here is another set I take a subset of R3 and I define W as, say, all the vectors of the form this. Okay. So, this is a subset of R3 because you see these contains all the vectors of the form 1 0 0, 2 0 0 to 1.300 like this, all this set. So, basically if you draw since it is in R3 you can draw a 3D plot, right. So, if you draw it like this, so this is your say x, y and z. So, in this case you will see what is R3? R3 is this entire 3-dimensional space, okay, and what is W? W is this line, right. Any vector in this line, any point in this line represents a vector, right. So, if you take a point here, this is a vector, right. You take another point here, this is a vector. What will be the, so if I ask you what is this vector, this is something alpha 0 0, right, because there is no y coordinate or x coordinate in this case. So, this set W is this entire x axis, right. It is the entire x axis inside R3, correct. And now notice that it turns out if you take two vectors here, if you add them up you will get another vector here. If you take a vector here and multiply with alpha you will get another vector on this line itself. So, it turns out that it can be shown that this W is indeed a vector space. You can actually go ahead and show that all the 10 properties, okay. But the good news is that if you have to show that something is a subspace of a vector space, okay, you just have to check two properties, okay, and those two properties are these, okay. First you have to show that W must be non-empty, okay, and secondly you have to show that if you take two elements from W, then V1 plus alpha V1 must also be in W. Basically it should be closed under scalar multiplication and it should be closed under vector addition. If you just show these three properties, the other the 10 properties will also get satisfied, and this can be proven actually. It can be proven that if you have to show that a set is a subspace, you just have to show these two properties and you are good to go, okay. And in our example that we took, the example that we took was this, right. Is W non-empty? Yes, W is non-empty, right, because I know that 0 0 0 is an element in W, right. Second is if I take two elements from W, so let me take the first element to be say A1 0 0 and say the second element to be A2 0 0, and now if I add them up, so this is your V1, this is your V2, if I add them up I get A1 plus alpha A2 0 0, which is this vector is also an element in W, right. So, that means that the second property is also satisfied, that therefore, the x axis which is sitting inside R3 is a vector space, or in other words it is a subspace of R3. Similarly, if you take the y axis, then the y axis is also a subspace of R3. The z axis is also a subspace of R3. What about the xy plane? Think about it. What about the xy plane? So, what will be the xy plane like? So, the xy plane, if you take the entire set of all vectors in the xy plane, it will be something like this. It will be something like this then. So, any vector in the xy plane can be written in this way, and notice that in this case also if you go ahead and check, you will find that this also is an element in W. So, the xy plane is also a vector space or a subspace of R3. The yz plane is a subspace of R3. The zx plane is a subspace of R3. Okay. So, in this way you can actually go ahead and construct infinitely many planes in R3 which will become subspace actually. You can always create planes. Okay. So, the idea of subspaces is similar to subsets. So, for sets you have subsets, but for vector space you have what is called subspace. What is the difference? For set we did not have any extra things to think about. In vector space it is not just a set, it has a special property that so that 10 properties that it had to satisfy over the scalars. The scalars in this case we are considering to be real numbers. In the same way is a subset of the vector space, and you will have the two properties, it is non-empty and it is closed under vector addition, and scalar multiplication will also be satisfied by that. So, now you see, if you are given a matrix, okay, suppose a matrix is given to you and the matrix is suppose an n cross m matrix. So, A belongs to R n cross m, that means A has n number of rows and m number of columns. Okay. So, if you have n number of rows and m number of columns, then using that matrix you can actually go ahead and create subspaces. Okay. And these subspaces are called fundamental subspaces of a matrix, and this becomes very important for us in this course. Okay. So, suppose you have this matrix A, again this matrix belongs to R n cross m. So, I can see that from there you can directly write that there are m number of columns. So, these are the columns of the matrix. Now, you can go ahead and define what is called column space or image of a matrix. What is column space or image of a matrix? So, the idea is, let me explain with an example. So, suppose you have this matrix. Suppose A is a matrix of this form, then what is column space? Column space is any linear combination of the columns of this matrix. So, basically if I take alpha 1, alpha 2, so then this is nothing but alpha 1 into 1, 2, 3 plus alpha 2 into 3, 4, 5, right, this is this. So, this set will be called the linear combination of the columns of the A matrix here, and this set is nothing but the image of the A matrix here. So, you give any value of alpha 1 and alpha 2, this will lie in this set, and the good thing about this set is that this will turn out to be a subspace. So, subspace of what? Subspace of R3. I have called this set to be image of A, right. So, this set is image of A, and notice that image of A, first of all it is a subset of R3 in this example, right. So, if image of A is a subset of R3, then first question, is image of A non-empty? Yes, because 0 0 0 belongs to image of A. If you take alpha 1 equal to 0 and alpha 2 equal to 0, this will be in the image of A. Similarly, I took 1 2 3 and I took 3 4 5, then you will see that this plus alpha times of this also belongs to this set. As a matter of the fact, you can take any element from the image of A. Idea is very simple. Idea is that if you have a matrix A which has, suppose in this case m columns, the set of linear combination of this matrix is a vector space over R, and or in this case it will be a subset of. So, image of A will be a subset of R n, right, because what are these vectors size? These vectors are of n cross 1, right. So, any element in the image of A must be an n cross 1 vector. So, image of A will be a subset of R n. The symbol that is used is image of A. In some books you will also find it to be column space of A. Why is it called column space of A? Because you are taking linear combination of the columns of the A matrix. This brings us to the next subspace that we can create with the help of the A matrix, that is called kernel of A. Okay, you remember this word, I had talked about this word when I was talking about generalized eigenvectors in the previous lecture, right, this kernel of A. Now, what is kernel of a matrix? So, kernel of a matrix, if you recall from the last lecture, is the solution set of Ax equal to 0. So, in this case A is a Again it is an n cross m matrix. So, when you might multiply A into x equal to 0, this is n cross m. So, this better be m cross 1 and this is an n cross 1 0 vector. So, collection of all the x which solves Ax equal to 0, all the vectors in Rm, okay, these will be vectors in Rm, x will belong to Rm. So, all the vectors in Rm which satisfies Ax equal to 0 is called the set of all those vectors is called the kernel of the matrix, or in some cases the null space of the matrix, and the symbol is kernel of A. Remember, in the last class we talked about eigenvalues. So, eigenvalues and eigenvectors. So, eigenvalues and eigenvectors satisfied AV equal to lambda V, which was nothing but A minus lambda I whole into V equal to 0. So, the collection of all the vectors which satisfies that satisfies this equation, we called it kernel of A minus lambda I, and all these vectors are nothing but eigenvectors. So, the set kernel of A minus lambda I were the eigenvectors of this matrix. You can see it directly, this idea of kernel of a matrix directly pops up here. For generalized case, it was A minus lambda I whole to the power of k, V equal to 0. So, how did we define generalized eigenvectors? Generalized eigenvectors was all of rank k was all the vectors which were in the kernel of A minus lambda I k, but so V must belong to this, but V must not belong to the kernel of A minus lambda I whole to the power of k minus 1. Right? This was how we define generalized eigenvectors of rank k. I mean, this I am recapping to emphasize that you see the kernel of a matrix becomes very important for us in this course. Okay. So, this is another subspace. If you take, for example, why is it a subspace? A quick check can tell you why is it a subspace. If you take Ax equal to 0, first of all, is the set of the solution of Ax equal to 0 non-empty? Yes, it is non-empty, because if you take x equal to 0, you know that Ax equal to 0 is satisfied. So, 0 is indeed a solution of that. That means 0 belongs to kernel of A. Okay. Again, what is this 0? 0 is an n cross 1 0 vector here. Okay. The second question is, if you take suppose a vector which satisfies Ax1 equal to 0, that means x1 belongs to kernel of A, and another vector say x2 which belongs to kernel of A. So, Ax2 is equal to 0, then you can see that A times of x1 plus alpha times of x2 is equal to A times of x1 plus alpha times of Ax2, but Ax1 is 0, alpha times of 0, and this comes out to be 0. That means x1 plus alpha x1, x1 plus alpha x2 also belongs to kernel of A, right? And this proves the second property, and that is the reason kernel of A is a subspace in this case. In a similar way, once you have the A matrix, you can also get the A transpose matrix, and for A transpose also you can talk about column space and null space of A transpose. That is also called what is called row space and left null space. So, till now I was looking at the A matrix as columns, right? Columns, there are m number of columns. Now I am looking at the A matrix with rows. Okay. So, there are n number of rows here. Okay, now you can see that if I take linear combination of these rows, remember when I talk of rows, it is in this form, it is horizontal form. You can always write this row in this form, right? This is one vector, this is another vector, this way this is another vector, right? So, these are the rows of the matrix A. Correct. Now, you can take linear combinations of this, that will be what is called as the row space of the matrix or the image of A transpose. An example can be, again, if I take A equal to 1, 2, 3, 3, 4, 5, then the rows in this case are 1, 3, 2, 4 and 3, 5. Okay. So, image of A transpose or the row space of this matrix is nothing but the linear combinations of the rows of the matrix. So, the linear combination of the rows of the matrix here, which is alpha 1, alpha 2 and alpha 3 becomes equal to real number. These are from real numbers. So, this is the row space of the matrix, and you can see that this will be a subset of R2 in this case. okay, which means this image of this is a subspace of R. What will be it be a subspace of R M. Similarly, you can talk about left null space of the matrix, because if you can talk about A x equal to 0, you can also take A transpose and talk about A transpose of y equal to 0, right. This is nothing but y transpose of A equal to 0. So, basically you can take a matrix, say you take a matrix 1, if you take a matrix say 1 2 say minus 1 minus 2, this is a matrix, say you can multiply from the left by, in this case by 1 1 to get 0 0, then we will say that 1 1 belongs to the left null space of this matrix. Whereas, if you take 1 minus 1 this, 2 minus 2, if you multiply from the right by 2 and minus 1, then in this case you will get 0, then we will say 2 minus 1 is in the right null space, or in general the null space of this matrix A. So, this also is a subspace, okay. You can go ahead and prove it, give it a try to prove that the left null space is also a subspace. So, you can see that given a matrix A, I can quickly create 4 different types of subspaces. One is column space created by the linear combination of the columns. Another is the kernel, which is created by the solution of A x equal to 0. Another is row space, which is formed using the linear combination of the rows of the matrix, and the last one is the left null space, which is basically all those vectors which when multiplied from left of the matrix A gives you 0, or in other words the kernel of A transpose is what is known as the left null space of a matrix. Okay. So, this is the idea about subspaces. So, what did we start with? We started with vector space, we got the idea of subspaces, we also learned the 4 fundamental subspaces that you can create with the help of a matrix. Okay. Now, we get to the idea of independence. I have talked about this independence idea in one of the lectures a bit. Okay. So, we will talk about that independence idea now. Okay. So, the first thing that we have to understand is what is called span of vectors. Suppose you are given 4 or 5 vectors, then the linear combination, all the elements that you can get by linear combination of these vectors is called span of a vector. What do you mean by linear combination? S is suppose V1 V2 to Vn, span of S is nothing but A1 V1 plus A2 V2 plus dot 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 An Vn, where A1 A2 and up to An are scalars. Okay. So, for example, if you take a set of this form, say S equal to 1, 4, 3, 5 and minus 2, minus 1, then the span of this is nothing but the linear combination of these 3. So, so the linear combination of these 3 means any vector which can be written as linear combination of these 3 will be in the set span of S. So, it's a very big set, it's a set which has infinitely many elements, okay, and that is what is known as span of S. So, you can think of it as that these vectors are generating that sets. Once you have a vector space, we can find out some vectors in that set which are linearly independent of each other. Okay. So, what do you mean by linear independence? Again, we talked about linear independence, right. So, linear independence was if alpha 1 V1 plus alpha 2 V2 plus dot 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 alpha and Vn equal to 0, then if the only solution that is possible for this is that alpha 1, alpha 2 and alpha n is 0, then we say that these vectors V1, V2 to Vn are linearly independent, right. This is what linear independence was. So, if you have a vector space and you can find out linearly independent vectors from there, okay, those linearly independent vectors will be generators of that set. So, for example, this was a set, right. From there I form this another set called span of S, which is basically collection of all the linear combination of these 3 elements, right. Now, span of S will turn out to be a subspace actually. In this case, span of S will be a subspace of R2. Why? Because you take, first of all, is it non-empty? Yes, it is non-empty. Second, you take 2 elements from span of S, add them up, they can also be written down as linear combination of these 3. So, span of S is a vector space is a subspace of R2, and span of S is created, is generated by these three vectors, right. Now, in these three vectors, you can see if you take V1 minus V2, you will get this vector, right, which means that this vector is dependent. This is dependent on these two. So, I can get rid of these vectors, and if I get rid of this vector also, even then these two elements can generate this entire set. So, if I remove this also, the set that you will get will be exactly the same set as span of the previous example that I showed. Point being is that if you have a vector space, if you have shown that it is a vector space or a subspace, because a subspace is also a vector space, you can always find out, at least in this case Rn over R, you can always find out finite number of vectors, linearly independent vectors, they are not dependent on each other, linearly independent vectors with the help of which you can create the entire space. Okay. So, basically these are the vectors, taking those, if you create, if you find out the span of these vectors, you will get the entire space. So, example, I think it will be better if I give you an example, because you can visualize what I am trying to say then. So, for example, let us take the case of R3. Okay. What was R3? R3 was a 3-dimensional space, right. So, this is a 3-dimensional space. So, R3 is say x, y, z. So, this is your R3 say. Okay. Now, I know that this is a vector space. I clearly know that this is a vector space, because we have seen that this over R is a vector space. So, if it is a vector space, by the logic that I have just now told you, I can find out finite number of linearly independent vectors from this space, which will generate this entire space. They can be seeds, they can be considered as seeds of this vector space. Using that, you can create the entire space. Okay. So, the example for this is 1 0 0. If you take this set 1 0 0 0 1 0 0 0 1, you see if I take this set, first of all, is this linearly independent? Yes, this is linearly independent. Okay. So, this is a linearly independent set, you can quickly check that. Okay. If this is linearly independent, and you can see that span of S, which is nothing but linear combinations of 1 0 0 plus 0 1 0 plus alpha 3 0 0 1, where alpha 1, alpha 2 and alpha 3 are real numbers. You can see the span of S is a vector space in this case. Okay. And not only that, any element in R3, you take any element in R3, that can be written as linear combinations of this. If you take, say, suppose 3 4 minus 1, then if you take alpha 1 3, alpha 2 4 and alpha 3 minus 1, you can get to this point. As a matter of fact, any point, which you can easily understand right now, that any point in R3 can be written down as linear combination of these three vectors, and these three vectors are linearly independent. So, we will call this to be a basis of the vector space. Why did I emphasize on the word A? Because you can come up with another set. For example, if I take 1 1 0 0 1 1 and say I take 0 0 1, say suppose I take this set. Okay. This will also turn out to be a basis for the same R3. Okay. Of course, a different basis vector, I can use these three to generate any element in the set. Again, you can check that these will be linearly independent. This has to be linearly independent. If I give you an example, so 3 4 minus 1, can I create 3 4 minus 1 using it? Yes, I can. You see, this is the linear combination that gives you this vector. Remember, although I am taking one example, this has to be true for any vector that you take in R3. It cannot be just for one example it works and then it does not work for others. That is not how it works. Okay, it has to be true for every vector in the vector space. So, therefore, we will call this linearly independent set as the basis, as a basis vector of the set. So, you can have as many number of basis vectors. Okay. So, for example, in R3 you can have infinitely many sets of basis vectors. Okay. But you will see eventually that the number of vectors in that set of basis vectors will be always 3. Okay. That is why this is called a 3-dimensional vector space. Okay. So, here is the formal definition of basis of a vector space. Basis of a vector space first must span the vector space. That means, any vector in that vector space must be written down, we must be able to write it down as the linear combination of the basis vectors, and secondly, the basis vectors must be linearly independent. Okay. And the dimension of a vector space is the number of vectors in a basis is called the dimension of a vector space. Remember I just now told that the x axis is a vector space in R3. So, the x axis was this, right. This was the x axis sitting inside R3, right. So, since it is a subspace, it is a vector space also, that I can talk about basis also. Now, if I ask you can you give me a basis vector that will generate this set? Yes, you can. So, the basis vectors will be 1 0 0, and you can see that the span of 1 0 0 is W. Any vector in W now can be written down as a linear combination of 1 0 0. Even you can even take something like this, span of 100 0 0 is also okay. So, 100 0 0 is also a basis vector. Okay. Here is a work for you. If I give you this set, think about it on your own. Okay, try to solve it on your own. So, this is the xy plane. If you remember, this is the xy plane. If I give you the xy plane, what will be a basis vectors for this set? Okay. Notice that in this example where I took the x axis, you see I got only one vector. So, this is a one dimensional space. You can call it like this. It is a one dimensional subspace sitting inside a 3-dimensional vector space, where R3 is a 3-dimensional vector space. So, it is sitting inside R3. Similarly, this will come out to be a 2-dimensional subspace. So, it is a 2-dimensional subspace sitting inside the 3-dimensional vector space. Okay. These words will become very important for us as we go along. Basis vectors, the dimension, all this will become very important for us. Then the idea of image, the idea of kernels will be very important for us as we move along. Okay. Now, another thing which is required for us is solving linear equations. Okay. So, if you have a set of linear equations, say Px equal to Q, where suppose P is a n cross m matrix and Q is a n cross 1 vector, and in this case of course x will be then m cross 1. So, if this is given to where P is known and Q is known and you have to solve for x, this is nothing but the set of linear equations, right. And you by now you should know that this is solvable if the rank of P and Q is equal to rank of P. Once this condition is satisfied, then you can also say that if the rank of PQ is equal to rank of P is equal to the number of unknowns. Okay, what is the number of unknowns? M number of unknowns suppose, then we will get an unique solution. However, if the rank of PQ is equal to rank of P is less than the number of unknowns, you will get infinite solutions. This entire thing can also be written down in terms of image of matrices. Now, Px equal to Q will have a solution if Q belongs to the image of P. Why? Because when you are solving Px equal to Q, what are you basically doing? P is these columns, right? Suppose these are columns of P, and then you are multiplying here the unknowns. Suppose you have m number of unknowns, okay, and this is equal to Q1, Q2 dot Qn. This is an n cross 1 vector. This is an n cross m matrix, and this is an m cross 1 vector, right? Now, if you need to get a solution here, that means this vector Q can be written down as x1 times of the first column C1. Suppose this first column is C1, this is C2 and this is C3. So, basically you are saying that dot up to xcm. Basically, you are saying that Q vector here can be written down as linear combination of the columns of this matrix A. Okay. So, that means Q must be in the image of P. So, a solution of Px equal to Q exists not. So, one condition is that rank condition, rank of PQ is equal to rank of P, but also if Q belongs to the image of P. Okay. So, this is an equivalent statement. Okay, you can talk about the solution of Px equal to Q in this way also. So, Q must belong to the image of P, then only there will be a solution. If Q does not belong to the image of P, then you will never be able to find out a solution. Further, you can see that if suppose Q belongs to the image of P, then I know that it will have a solution. Then the question is, will it have unique solutions or in infinite solutions? Okay. So, it will have unique solution if the kernel of P is trivial, which means kernel of P is nothing but only the 0 vector. So, okay, and you will have an infinite solution precisely when your kernel of P is non-trivial. So, you see the same ideas that x equal to q, the rank ideas that you already know of can also be written, also be told from the perspective of subspaces. Okay. And this will also become very important for us as we move along, because so whatever we will do next will involve lot of linear equations, solving linear equations. Okay. And when it comes to linear equations, where the first question that you always ask is whether it is solvable or not. If it is solvable, then does it have a unique solution, does it have a non-unique solution? Okay. All those questions you always ask. So, this brings us to the end of the basics of linear algebra that will be required for this course. Of course, as I already told, it is not a exhaustive linear algebra course which or linear algebra ideas that is required in this modern control theory. However, these are things which will be very important for us as we move ahead, and you will see that these words will keep on popping up. So, in the next lectures we go back to system theory again, okay, and we will try to see what are the other things we can talk about in system theory, or how do we design controllers from the modern control theory perspectives, and you will see all these ideas that we talked about today coming into action in those concepts. Thank you.